We're going to be talking about section 2.3 today, which is talking about set operations and Cartesian products. We're going to be talking about intersection of sets, unions of sets, difference of sets, ordered pairs, Cartesian product of sets and Venn diagrams, and De Morgan's law. So to start with, we're going to be talking about intersection of sets. When we intersect two sets, we're looking for elements that are in both of the sets. So you might be familiar with a Venn diagram, and with the Venn diagram, you have your universal set. You have set A, and you have set B. And with the intersection of the sets, the intersection is where A and B overlap. So in that case, it would be this area right in here. So with intersection of sets, they're looking for the elements that are in both sets A and B. So if we looked at these two problems and we wanted to find the intersection of the sets, we want to look and see what's in both sets. So we'll start with the first set. We'll notice that 1 is in both sets. 3 is in both sets. 5 is in both sets. And so the intersection of set A, or the first set and the second set, would be the numbers 1, 3, and 5. In the second example, we'll notice that the 3 numbers in the first set, 2, 4, or 6, and the second set is the null set. So there are no pieces in common. So the intersection would be, again, the null set. So that's what our solutions are. The solution for the first answer would be 1, 3, and 5. Those are the pieces that they have in common. And the second solution would be the null set. Now you'll notice the symbol for intersection is the upside down U. Okay. And so there's going to be another symbol that we're going to be talking about in just 1 second. And that symbol is for union of the sets, and the symbol for union is the letter U, or an upside down or a right side up U. With the union of the sets, what we're looking for is elements that belong in both sets. So they belong to either one of the sets. Either set can have the information. So if you think about the word union, what we're talking about is we're joining together the two sets, the union of the two sets. So again, let's look at our Venn diagram. And if we had a Venn diagram, this is the universal set. This is set A, and this is set B. So the union of the two sets would be all of the things that A and B have in common. So A and B have all of this area in common. They have this area in common, and they have this overlap area in common. So the union of A and B would be all of the parts of A and B combined. So if we look at this problem again and we say what's the union of the sets, we would have to make sure we took 1 of everything. So the 1 would have to come, the 2 would need to come, the 3 would need to come, the 4, the 5, the 6, the 7, there's no 8, and so then the 9. So the union of these two sets would be the numbers 1, 2, 3, 4, 5, 6, 7, and 9. If we look at the second example, the union of those two sets would be all of the numbers in the first set plus the null set. But there are no numbers in the null set, so our answer would be just the numbers 2, 4, and 6. So again, here's our answer. The solution for the union of the first set would be the numbers 1, 2, 3, 4, 5, 6, 7, and 9. And the union of the second sets would be 2, 4, and 6. All right, so when we're talking about the difference of the sets, that means that we want to take whatever is in set B in this example and take it away from set A. If I reversed it and I said B minus A, I would want to do the opposite and take whatever is in set B and take it away from A. I said that backwards. Whatever is in A and take it away from B if I switched it. So if I think about what that would look like in terms of a Venn diagram, so again, here's our Venn diagram. Here's the universal set. Here's A. Put a little A in that corner this time. And here's B. So if I want everything that's in A, but not in B, I want to take away the parts of B, then I would just have this part of the circle. I would not have this part in the middle where they intersect, and I would not have any of the B values. So let's look at these. We want to take everything that's in A, and we want to take away anything that's in B. So B has the value C. So that means we want to take the C out of A. It has an E, so we want to take the E out of A. And B has a G, but we don't have a G in the A. So if I looked at this, the difference between A and B would be the set of numbers A, B, and H. If I look at the second example, this time I want to take the values that are in B and I want to take away any of the things that are in A. So A has an A in it, but there's not one in B. A has a B. A has a C, so I want to take away the C. I want to take away the E. And I want to take it away in H, but there's no H in B. So B minus A would be the set G. And I want to union that, which means I want to join it together with all the things that are not in C. So let's go back up here. So the things that are not in C, I'm going to look at the universal set and take away all the things that are in C. So I'm going to take away the A, the C, the D, the G, and the E. So if I took all those things away, the things that are in the that are not in C are B, F, and H. Remember, we called that the complement of C. So if I join these two sets together, I should have the set G, B, F, and H. And that's what our answers are. You'll notice that the answer is written in a different order. It doesn't matter what order they're in, they are still equivalent. So now we're going to look at ordered pairs. And an ordered pair is always in the format of AB, where A is the first component and B is the second component. Just like when you're graphing ordered pairs on a graph, if you remember doing that, the value of A comma B is not the same thing as B comma A. So two components are equal only if their first components are equal and their second components are equal. So we would be looking at that to make sure. So something that we have here is called a Cartesian product of sets. And what a Cartesian product of sets is when you're basically taking all of the values in one set and matching it up with all of the values in the other set. So in this case, we're going to take all the values in A and match them up with all the values in B and come up with a set of ordered pairs. So let's look at this example. If I want to find A cross B, then what I'm going to do is I'm going to take all the values in A, which are A and B, and I'm going to match it up with the values in B. So if you want to think of it as almost like a distributive, we're going to take A and match it with the 1, and then A and match it with the 2, and then A and match it with the 3. And then we're going to repeat that, but we're going to take B and match it with the 1, and then B and match it with the 2, and then B and match it with the 3. So we'll end up with the ordered pairs A, comma 1, A, comma 2, and A, comma 3. And there's 3 others, but I'm going to stop there with that one. And then what we're going to do for the next step, for the next part of the question, is we're going to match up all the values of B with all the values of B. So let's put up another set here. So here's B again. So we're going to match all of the values of B with all the values of B. So we're going to do 1 with 1, 1 with 2, and then 1 with 3, and then we're going to match 2 with 1, 2 with 2, 2 with 3, and then we're going to do the same thing with the 3's. So these are our solutions. So again, we have the set A1, A2, A3, and then B1, B2, and B3. And then for the second one where we're doing B cross B, we're going to have 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and 3, 3. So when we're looking at cardinal numbers, if the cardinal number of A is little a and the cardinal number of B is little b, then the number of elements, or the cardinal number of A cross B, would end up being the same thing as B cross A. And all you're going to do is take the cardinal number of A and multiply it by the cardinal number of B. So you end up with A times B. So if I had, for example, going back to that problem, I had 2 elements in the first set and 3 elements in the second set. So the cardinal number of A was 2, the cardinal number of B was 3. 2 times 3 is 6, and there were 6 elements in that set. Whereas on this one, the cardinal number of B was 3, the cardinal number of B was 3. 3 times 3 is 9, and I had 9 elements in that set. So if I say the cardinal number of A is 12 and the cardinal number of B is 7, then the cardinal number of A cross B would be 12 times 7. And again, you'll notice that the cardinal number of B cross A is the same thing. It would be 7 times 12, which no matter which way you do it, whether you do either way, it's 84. Okay, so then these are just, we talked about this already, some different Venn diagram representations. If we're looking at the first one, again, this is the intersection, or and. You can use the word and also to help represent that. The intersection, or and, is when they overlap. The union between A and B is the word or. And again, it's the union, and you can remember that because of the letter U. The complement of A means all the things that are not in A. And then A minus B, or the difference between A and B, is the Venn diagram that you see here. So what if I said draw a Venn diagram to represent the solution set of A, the complement of A, and the and B. So we're looking at the complement of A intersected with the values in B. So if you'll notice in our graph down here, what we have, the values of B are all of the things in this region here. Okay, and I've got that blue stripe in there. A complement are all the values that are not in A. So A complement would be all of this area out here, including this part here that's not in the A circle. So what we're looking for when we're looking at the intersection, which is the upside down U, what we're looking for with intersection is where do these lines overlap? And you'll notice in the shaded region that's the area that's overlapping. So here's another one. Draw a Venn diagram that represents the complement of A intersected with the complement of B, and all of that intersected with C. So let's look at what we have here. So the complement of A, let's start with that one. We're going to do that in red. The complement of A is all of this part of the graph that's out here. I'm going to get a little messier here. The complement of A is all of this part out here in red. Okay. The complement of B, we'll do that in this color blue. The complement of B is all of this part out here in blue. Okay. So you'll notice right now there's some overlap over here. There's some overlap down here. There's some overlap down here. Over on this side, that's all overlapping. There's no overlap inside of A at this point in time. There's no overlap. If you look at this black circle here for A, there's no overlapping in there. And right now, there's no blue, there's no overlapping in here. Okay? So right now, if we look at where these two parts intersect, what we have is, where are they intersecting? You'll notice that the parts that they're intersecting at are just this outside part here. So if you look at A and B, here's A, here's B. Right now, our only overlap is this part of the graph out here. Okay? Now C is this circle that we're throwing in right here. And you'll notice that C overlaps right in here. So when we're looking now for the intersection of the black part that's overlapped and C, we end up with this graph that you see as our solution. You'll end up with that part of it there. And that brings us to something called De Morgan's law. And what that says is that for any set A and set B, the intersection of A and B, the complement of that is the same thing as the complement of A and the complement of B unioned. And if you think about the opposite one, the union of A and B's complement is the same thing as the intersection of A complement and B complement. So we can use De Morgan's law to simplify some of our work a little bit, like with that Venn diagram. If we go back to that Venn diagram and use De Morgan's law on the Venn diagram, this part of the picture right here would be the same thing as A intersect B, the complement. Okay, so what we're doing is we're saying A intersect B is this part of the graph right in here. So the complement of that would be everything that's not in that area. So the complement of that would be this part of the graph over here in green. And then if we intersect with C, where does the green overlap with C? You'll notice that the green overlaps with C. Let's do blue on that color. The green overlaps right down here. So again, that's using De Morgan's law. I hope this is helping a little bit. Let me know if you're having any problems with this, and we'll work on those problems. Have a good day.